Yeah. Now, this is the thing what you will be seeing. So the book for system software is Leland L. Beck, the third edition. The third edition will do, and recently the other edition is also available. But other than this, this is the syllabus. The module 1 and module 2 is our system software. Fine. So which we're going to be seeing the first module, the assemblers and the macroprocessors. In the second module, we'll be looking at loaders and linkers. Please mute yourself, whoever has joined now. Okay. So what and all we'll be seeing today's class is introduction of system software and how it is related to the machine architecture. Two hypothetical machines we'll be discussing. One is SIC, that is Simplified Instruction Computer. The other one is the SIC XC, right? That is right. It is an upward computable machine wherein we'll be having the SIC features also, as well as the SIC XC features also, which is bit advanced features, right? Why we need to study these machine architectures is the reason is when you studied a microprocessor, you use the 8086 as a reference machine. So architecture, instruction set, addressing modes, everything relevant to that particular machine. But here for system software, we don't have such sort of thing. For that reason, we'll be using the SIC XC, SIC and SIC XC machines. Fine. Okay. So the system software, what is it? It's a set of programs that is used for operation of the computer itself. So it doesn't provide you any functionality. It is supports the operation of the computer itself, means at the back. So if you think of the system software, it can be either implemented as a software, for example, your operating system, or it can be implemented as a firmware, means as part of your between hardware and the computer, means a hardware and the software, right? So something like your what do you call BIOS. BIOS is also a system software. So either as a software or as a firmware, it can be implemented. So the system software is machine dependent. So majority of the features are machine dependent. So participants, those who are joining now, please mute yourself. Right? Okay. So majority of the features of this is means system software is machine dependent. Fine. Okay. Right. Yeah. We proceed further.
ಬರ್ತಿದ್ಯಾ ಇದು ಸೌಂಡ್ ಬರ್ತಿದ್ಯಾ ಸರ್ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡೋದು ಫ್ರಮ್ WeChat.
Okay. Right. The next thing is so they are intended to support the operations of the system itself or computer itself. So rather than any particular application. So that's what is the system software means. Here are some of the examples what we do have. Those are your editors, your compilers, loaders, linkers, debuggers, macroprocessors, operating system, BIOS, all these things comes into this category of what do you call comes into the category of your system software. Fine. Right. We'll proceed further. So this is the architecture. What we can have a look at that. The user and the application program stands at the upper level, and those application programs will talk to your system softwares, and then the hardwares are moved accordingly so as to get your work done. For example, as I told you earlier, if at all I give a print command in my MS Word will not print. Instead, the print is transferred to the operating system. The operating system in turn finds appropriate device drivers and it runs the transducers, whatever is there in your printer, and your data is transferred through IO controllers and it is going to be printed. So this is how the interaction that happens. At the lower level, you will have the system software. At the higher level, you are going to have the application software. The application software talks to system software, and in turn, the system software talks to your computer. So there is a high level of machine dependency with your system software and means of your system software compared to your application software, right? All right. And the system software and machine architecture, here we should understand the machine dependent. There are few features of the system software which are machine dependent. For example, the instructions. If at all your compiler need to convert your code, it need to know the instruction set architecture, instruction format, addressing modes, what is the sort of assembly language that is being used. Similarly, these are some of the machine dependent features. Similarly, your machine independent features is general design, logic of how to implement. For example, the assemblers are implemented in 2 passes or 3 passes. So like that way, right? So as to understand this machine dependent and independent features, we will refer to hypothetical machines. One is SIC, Simplified Instruction Set Computer, and the second one is SIC-XC. So today's discussion is to learn about the architecture of SIC machine. Along with it, we'll also see the the instruction set of this particular machine, and we're going to write a program using the SIC machine. So that's what is the agenda of today. Right, we'll start with the SIC machine. Please understand the architecture you should be knowing, so as you can connect this when you are writing the programs as well as constructing the assemblers and all these things. So as I mentioned, SIC is a hypothetical machine, it doesn't exist. So it's a standard model, that's what we're going to use. So it comes in 2 variations, the standard model called as SIC and the extended version or extra equipment, which we call it as XC. These are the 2 versions what we do have, right? So, and SIC is upward compatible to SIC-XC. What I mean by that is, whatever the program you have written in SIC is able to or can be run in SIC-XC, but the reverse is not. The program written in SIC-XC cannot be run on SIC machine, right? So SIC-XC, extra equipment, right? We shall start with the architecture of SIC machine. So first we shall start with the memory. SIC is a simple version of the machine, and it has got a small memory. And here we will going to use the same earlier notation, 8-bit forms 1 bytes. So, and it is byte addressable. And 3 consecutive bytes form 1 word. 1 word, integer is also a word, and okay. And here we don't have a floating point numbers. So 3 consecutive bytes form 1 word. That is 24 bits is 1 word, right? And a total of 32,768 bytes we have. That is equal to 32 kilobytes of memory we have in SIC machine, right? And we do have registers. So on processor buffers, which we call it as registers, right? And here we do have 5 registers. Each register size is 24 bits, right? Each register size is 24 bits, and it's a standard, right? Okay. And these are the set of registers what we have. Every register is given a symbol as well as a number, right? Given a symbol as well as a number. Okay. The first register is called accumulator, which is given a symbol A, and the register number is 0. Accumulator's number is 0. Second register is called as index register, which is given the name X, and its number is 1. Link register, which is used to make jumps as well as subroutine calls, which symbol is L, and the number is 2. And the next we do have is a program counter, which always keeps track of the next address of the instruction to be executed, whose number is 8, and the status word, whose number is 9. So this is it. You can see that the accumulator, index register, link register, we have the numbering starting from 0, 1, 2, that's fine. But there is a missing numbers in between after 2. There is 3 to 7, there are missing numbers. What are these missing numbers? These are nothing but the additional registers what we have in SIC-XC, which is not present in SIC machine. So when we discuss the architecture of SIC-XC, you can see the missing numbers will going to be filled there, right? So we have additional registers in SIC-XC, which is not there in SIC. Fine. Okay. So we continue with the architecture. Data formats. Here we have mainly two data formats. One is integers, which is of 24 bits, or 3 bytes, or 1 word. Either of the way you can think of it, right? And negative numbers are represented by 2's complement, just as in all other wishes it is represented in 2's complement. Here also it is represented in 2's complement. Characters are 8-bit, and we use ASCII encoding, and it is a 8-bit ASCII representation. As I mentioned, there is no floating point numbers because there is no floating point hardware implementation in the arithmetic unit of SIC. So either we can perform the operation character to character or integer to integer. That's all. So that's the capability of our SIC machine, right? So why is it so? Because we don't want to complicate the architecture. Our intention is to understand about the system software, machine dependent features, not concerned with the hardware, right? So that's the reason. Fine. Okay. Right. Right. Instruction format. Here we have only one format of instruction, but in SIC-XC we have 4 formats of instruction. Here we have only one format of instruction. There is 24-bit format or 3-byte format we have. We have an X bit. One bit is designated as an X bit. The X bit represents the index addressing mode is used or not. Means if this X bit is 0, you can see the diagram. If the X bit is 1, it indicates yes, index addressing is used. If not, if X bit is 0, index addressing is not used. And 8 bit is used for opcode, higher order 8 bit. The lower order 15 bits is used to specify the address. 2 to the power of 15, we can address 32 KB of memory, and each address is byte addressable. So 15 bits is enough for addressing all the 32 KB of addresses. So that's how it goes. So we discussed about registers, we discussed about data formats, these two things we have, and we discussed about the memory, right? So you should be remembering this, right? And addressing modes. As SIC is a simplified machine, so we have simple addressing modes. We are using only 2 addressing modes. One is the direct mode, wherein the 15 bits address is completely given in your instruction itself, right? Okay. Second one is indexed addressing mode, which is represented by X, right? Wherein, right? And this is how the target address calculation will happen. If it is a direct addressing mode, target address is equal to the entire address itself, right? While if it is indexed addressing mode, target address is equal to yes. Drawing is not a drawing board for you people to draw these things. If you are not interested, please leave the meeting. Please do not disturb. Are you able to get the things? Please clear the screen, whoever has did it. Please clear the screen, or else I'll going to disconnect the meeting. Hello. Hello. Please clear the screen, whoever is doing this. Hello.
There is the option called annotate. You need to disable it.
Where is it?
In the view options, you can get the annotate option. Only host can disable it, and you can clear the screen also.
Where is it? Is it in manage participants?
I think so, got it, sir?
Yeah.
And you can clear it from there only. That annotate option.
There is no clear option here.
It is there, sir. For host, it will be available. You can clear everything.
They show names of annotators. Yeah, thank you. Right. Yeah. Okay, we shall proceed with this. As I was talking, there are only two addressing modes we do have. One is direct addressing, wherein the address is given directly in the instruction itself. The second one, where is the indexed addressing, wherein the X bit will be made 1 and the target address is calculated by not only the address given in the instruction, address plus the contents of the register X, both together will going to give you the target address. So this usually will be used for working with arrays, right? So we shall move further. Next instruction, so we'll talk about the instruction set of the SIC machine. So first category of instruction is the data transfer instruction, wherein we're going to see the load instructions and then the store instruction. Load instructions usually used to transfer the data from memory to registers, from the memory to the registers. And usually data transfer rate means data transfer is 24 bits at once. And load can be direct also, and it can be indexed also. If X bit is 1, it is going to be indexed. So, but we do have a special instruction called LDCH, which is only transfers the data 8 bits, loading a character. You can load 1 character or 8 bits from the memory to the what you call registers. So we shall see some examples, whatever the instructions we do have. LDA means load accumulator. The M there is a memory location, whatever the variable name you have declared, that is going to be used here. Now the contents of M, that is 24 bits, is transferred onto accumulator, right? So the same version with the indexing, LDA M comma X. Now contents of X is added to the address of M. The resulting M, I mean the resulting target address will be used, or will be loaded onto your accumulator. Right. Next is You can similarly load with other two registers also. That is the X and L registers. LDX M, the memory contents is loaded onto X register. Similarly with indexed addressing mode, X contents will be added with the address, M address. Whatever the resulting target address, its contents will be loaded onto X. LDL can load to L registers, 24 bits is loaded onto L registers, and LDL M comma X. So wherein target address is calculated by adding M and X, and that will be loaded onto your L register. Fine. Further we'll move on. We have LDCH, one character that is specified in the variable CH, 8 bits will be moved on to your accumulator. Fine. Similarly, LDCH comma X means that is load character with indexed addressing mode. X will be added with the address of CH. The resulting target address will be one character, 8 bits will be loaded onto your accumulator. Right. So there is I don't means you may feel that this much detailing of the instruction set we may not be needed, but yes, it is needed when we are constructing our assemblers. So this and all are the very basic fundamentals which must be known. So that's why I'm stressing upon this particular. So we do have data transfer instructions, store instructions. The next data transfer instruction is store instruction, which is used to transfer the data in the reverse order. That is from the register to the memory. Again, here the standard is 24 bits. Store can be direct or it can be indexed addressing mode. We have a special instruction called STCH, which is used not for 24 bits, but for 1 byte, that is 8 bits to be stored. Fine. Store instruction STAM, store accumulator contents onto memory location M, and with indexing, same as contents of A is transferred to that address, which is obtained by adding contents of X with the address of M. Similarly, we do have STX here, X register we are using, and STL, L register we are using. Similarly, we have STCH, store character, which is of 8 bits. Contents of accumulator will be moved on to M. And see there, whenever we are loading a character, it will be, you cannot directly load it into any of the registers like X and L. You can only load it onto accumulator, right? And when you are storing a character, the character must be first present in the accumulator and then it is supposed to be transferred. That's how it is working. So the indexing way of storing a character, STCH M comma X, wherein accumulator is stored to that memory location, which is obtained by adding contents of X with address of M. So this is the thing, right? We have one more special instruction called STSW, which is a 24-bit, not a 8-bit, it's a 24-bit. STSW is store the status word. Store the status word. Status word contains the conditional codes, which will be set after execution of every instruction. So this conditional code specifies whether the result of previous operation is a greater than, less than, or equal to. So this means the negative flag or positive flag or zero flag need to be set. So that's how the STSW will going to be used, and we can store the contents of status word onto a memory location also, right? That's what can be done through STSW instruction. And remember, it's a 24-bit instruction, means 24-bit data transfer, not a 8-bit. Okay, next we move on to the arithmetic instructions. We all very well know, but one thing important here is that when you are performing arithmetic or logical operation, one of the operand must be present in the accumulator. Other can be another register or other can be a memory location, must be a memory location here, because SIC doesn't support register to register operations. It supports register to memory operations. Fine. So one operand must be your accumulator, other operand must be your memory location, right? So result by default will be stored in your accumulator. Result of the arithmetic operation will be default stored in the accumulator. That's what is the thing. As other operations, arithmetic can also be a direct operation or it can be an indexed operation. And usually what I mean by indexed is you are working with arrays, then the indexing addressing mode will be used, because we're going to be accessing the elements in a continuous manner. So only the index need to be changed. The starting address remains to be same. So, but if it is a direct address, you are just accessing one variable, right? So such cases we are using only the direct addressing mode. But if it is more an array operation, it will going to be an indexed addressing mode, fine? Okay. Yeah. So first example, add m, contents of accumulator will be added with the memory, result is stored in memory, right? So the same with indexed addressing. Now the address of the memory location is an effective address which is obtained from adding the contents of X register with M. That will be added with the contents of A and the result will be stored in A. That is your accumulator, right? So, and then we have subtract operation similar to it. The indexed version, sorry, this is multiplication, supposed to be a subtract operation, right? So a multiplication operation, multiplication with indexing. Right. And similarly, the division operation and the division operation with indexing. Right. These are some of the arithmetic operations what we can have. Next, we have the logical set of operations, wherein logical operations also need to be have one of the what you call operand in accumulator, other in memory, and the result will going to be default in accumulator. So something like this, AND operation or operation. We don't have NOT operation. We do have only AND and OR operations provided by SSH. Okay. So TIX instruction, I think we're going to stop after TIX instruction. TIX is a special type of comparison instruction, which is a logical instruction. Okay. What this TIX does, just observe the sequence. TIX increments the contents of X register, whatever the contents of X register, which will be incremented by 1, right? That's the first task what your TIX is. Next is after it is incremented, the new contents of the X register will be compared with the memory location, right? When it is compared with the memory location, three possibilities. Either X is greater than M, or either X is less than M, or either X is equal to M. So based on this, we are going to have the conditional code flags set, right? That's what is the TIX test. See, TIXM, X plus 1 it will do, then it will do X minus M, so as to do the comparison, right? X is compared with M, X minus M it will do. X minus M, if it results 0, it is equal. If it is 0, 0, it is equal. If it is 0, 1, X is greater than M. If it is 1, 0, it is X is less than M. This instruction will be widely using while writing the program, because we usually put the count, anything that we need to count. For example, I am reading an array or writing into an array. I want to write 10 characters. The count 10, we're going to be putting it onto the X register. And we can keep on, means what we can keep on comparing it, whether we have reached the end of it. So that's the importance of X register, fine? So this much as we are running with free versions of your what you call we are running with free version of our Zoom. It only allows the 40 minutes of our what you call session. So I am stopping here. The next class will be scheduled and will be informed to you. Thank you.
Thank you, sir.